Hello everyone, I Nikhil welcome you to Vigyan Bharat. In this video, I'm going to discuss problem number 16 from TIFR GS 2021 Mathematics Entrance Examination. This is a very simple problem based on a matrix. We have to answer whether the given matrix is diagonalizable or is it nilpotent or is it idempotent or the none of the above options are correct. So let's move ahead into solution of the problem. If you see, in order to answer any of the three options, we should know what are the eigenvalues of this matrix. And to know the eigenvalues of the matrix, we will going to calculate its characteristic polynomial. So I assume my given matrix to be A. The characteristic polynomial of this matrix A is given by determinant of this matrix A minus lambda I3, where I is the identity matrix of order 3 by 3 I3 and lambda I assume is my eigenvalues. When you're going to substitute or when you're going to evaluate this expression, this matrix is going to look like this. Basically, I have subtracted lambda from the diagonal of this matrix. Now when you're going to expand the determinant of this matrix along row 1, I have expanded. So this will be the first computation. This will be the second computation. After simplifying here, if you go on simplifying this expressions, your characteristic polynomial is going to look like this. Now we try to factorize the above equation. Clearly, if you see from the constant term minus 2, it's pretty clear that one of the divisor of this constant, that is either 1, minus 1, 2 or minus 2, will be a root of this equation. That is a very standard result which we have learned from our elementary classes. So if you here substitute lambda equal to 1, it will be going to be satisfy this equation. And from this observation, now it's quite easy for me to factorize this equation. Since lambda equal to 1 is the root of the equation, so lambda minus 1 will be a factor. So now again here I am factorizing this equation. See, from the first term I am taking lambda minus 1. Because I have to take this factor common out, I have split my square term as minus lambda square minus 3 lambda square. Now you can factorize it, it's very elementary. Lambda minus 1 will be going to be common in these two. So if you take it out from all the three, the resulting equation will be going to become like this. When you're going to simplify it further, your factors will going to look like this. You will going to have lambda equal to 1 twice and this lambda equal to 2 once. Now we know that determinant of any square matrix A is given by the product of its eigenvalues. Since these are our three eigenvalues 1, 1 and 2, so the determinant is given by the product of these three, which will be simply going to have to be 2. So of course the determinant is non-zero. Just from this observation now here that all the eigenvalues are non-zero, we can easily discard option B, that the matrix is nilpotent, which is going to be incorrect. Why? Because the eigenvalues of a nilpotent matrix are only 0. A nilpotent matrix cannot have any eigenvalue other than 0. This is a very standard result which here I am asking you to prove why the eigenvalues of a nilpotent matrix are 0. Use the definition of what is a nilpotent matrix. Nilpotent matrix means I call a matrix N to be nilpotent where n is some square matrix. If n raised to the power k, where k is some positive integer, is 0, the 0 is 0 matrix, that is k is the least positive integer, so that when I raise my n to this power, I get the 0 matrix. In this case, I called this matrix n to be nilpotent and this small k to be the index of nilpotency, that is the least positive integer from where I am getting the raised to the power this n. If I raise to the power this matrix n to the power, that is if I raise the matrix to the power k, it gives me 0. That if I multiply my matrix k times, it's going to be 0. And of course, all the higher powers will also be 0. So this is the definition of nilpotent matrix, and you have to prove why the nilpotent matrix has only 0 eigenvalues. So clearly option B is now discarded. Now I'm checking another option. Here I have computed a square, that is a times a, and when I was calculating, I got my first entry to be 10, which is not equal to a, because the first entry in the original matrix were 4 and in the a square the first matrix is 10, so I don't need to compute further. Clearly a square is not equal to a, so option C is also incorrect, that is a is not idempotent. A is not idempotent. My option C is also incorrect. So I have discarded now two options, option B and option C. Now since these two are incorrect, now I'm left with, I have to check for A, whether this matrix is diagonalizable. So in order to check for this matrix whether this matrix is diagonalizable or not, I have to use some of the standard results which we know how to check whether a square matrix is diagonalizable. By definition, we say a matrix A is diagonalizable if you can find a basis consisting of eigenvectors for the matrix, and here if you see the other criteria is if the eigenvalues of a matrix are all distinct, then which implies that the matrix is diagonalizable, but in our case the eigenvalues are not distinct, so I'm going to use the final standard result, which says that the algebraic multiplicity of each eigenvalue if equals to its geometric multiplicity. By geometric multiplicity mean for any eigenvalue the dimension of its eigenspace, number of eigenvectors corresponding to that eigenvalue. So if you see here, for lambda 1 equal to 1, its algebraic multiplicity is 2. I have to calculate what is the geometric multiplicity, that is the dimension of this null space, dimension of null space of A minus the eigenvalue times the identity matrix. Similarly, I have to calculate the geometric multiplicity for lambda 2 equal to 2 using the definition. So there are two ways to calculate this. First is directly you calculate first the null space. So for the first case in which my lambda 1 equals to 1, I am calculating first this matrix inside A minus I3 simply. So this is A minus, this is the 3 by 3 identity matrix times 1, so it is same as this. Simplifying, we are going to get this matrix. I assume V to be a vector in R3. Of course, this I assume V to be non-zero, because in order for this to be an eigenvector. Now, in order to find my null space, I use the definition again. I am looking for all those V's such that this matrix times the vector gives me the 0. The 0 means this is the 0 vector in R3. So this expression is going to look like this. If you are going to simplify this matrix product, you will see on the left you are going to get a system of linear equation in which, if you see, equation 2 and equation 3 that is going to come out are nothing. Equation 2 is same as equation 1, and equation 3 is going to come out to be 3 This is again, this equation 1 is 1 by 3 times of equation 1. So I can discard equation 2 and equation 3 because they are just scalar multiples of first equation. So that's why I have written the first equation only here. You can take 3 common out from here, so this is going to look like this. And when you're going to here, from here you're going to find the value of A in terms of components B and C. Your original vector was this A, B, C. Now I have replaced A by B minus C. If I separate this vector in terms of the linear combination of these two vectors for scalars B and C, of course these A, B, C are coming from R, and of course they are non-zero, so they cannot be zero because they cannot be zero simultaneously, because I have assumed that this is a non-zero vector in order for it to be an eigenvector. Now every vector in my null space can be written as a linear combination of these two, that is, and clearly these two are linearly independent as they are not scalar multiple of each other. Clearly V1 and V2 are linearly independent and the null space is spanned by these two. So these two vectors forms the basis for this null space, and therefore dimension of this null space comes out to be 2. So if you go back, you see here that this option comes out to be 2. So our first requirement is met, that is the algebraic multiplicity of the eigenvalue lambda 1 equal to 1 is 2, which is same as its geometric multiplicity, which means that for lambda 1 equal to 1 there exist two eigenvectors. This 2 means there exist two eigenvectors V1 and V2 corresponding to the eigenvalue lambda 1. Finally, I have to check for lambda 2 equal to 2, as its algebraic multiplicity is 1, that it comes one time in the characteristic polynomial. Now if I am able to show that this is 1, if I am able to show that, then my job is done. So I'm going to calculate this thing I have to find. Now this thing I can find using now directly the rank nullity theorem, because this is also a matrix. This is a matrix. So dimension of null space of this, see how I have found this. Dimension of the null space is same as n minus rank of, this will not be rank, it will be dimension of the rank of, this will be dimension, wait, no, this is fine, it is fine. If I have written range space, then in that case I have to take the dimensions, but since I am writing rank, then it is understood rank is simply the dimension of the range space of A minus 2i3. This, why they are equal? Because of the rank nullity theorem. So dimension of the null space, I have to calculate this thing, which is same as n minus rank of this. N is 3 in our case, because this is a 3 by 3 matrix, A minus 2i3, and if I have to express in terms of a linear transformation, I'm going to take a map from R3 to R3. So this is my 3, which is coming up to be here n, minus I have to calculate the rank of this matrix. Now it's pretty straightforward, you can easily calculate the rank. First find, in order to find the rank of this matrix, I have calculated A minus 2i3, that is from the original matrix. I have subtracted 2 from the diagonal. Now I'm applying some elementary row operations, which is quite straightforward and easy. Here I have interchanged the rows. What I have done, basically, this first row go on to this place, this comes to the second place, and the second row comes on to the third place. That's how my matrix looks like this. Now what I have done here, R2 changes to R2 plus 2 times of R1, and R3 3 times of R1. These are two elementary operations which I can apply. After simplifying, the matrix will look like this, and from here it's pretty clear that since this is now an upper triangular matrix, and the elements on my diagonal, the first two elements, these are my pivots, here, which I have marked by circle. So rank of this matrix is 2. Because now the rank is 2, so if I go back again, then this comes out, wait, no, this is 2. I'm going pretty fast. This is 2, yeah. Now from here I'm going to calculate dimension of my null space is n minus the rank. This 2 comes out to be here, so 3 minus 2, you get 1. That's all. That's what I was looking for. So if I go back, if you see here, the geometric multiplicity for the eigenvalue lambda 2 equal to 2 comes out to be 1, and its algebraic multiplicity is also 1. So now I met the requirement for a matrix to be diagonalizable, that the algebraic multiplicity of each eigenvalue equals the geometric multiplicity. So clearly now the given matrix A is diagonalizable and A is the correct option. If we go back and see here, now this is the correct option. So I hope you have understood the solution to the problem, and just a useful information before concluding, that if you find this video to be useful, then do give us a like, and you may also join our Telegram group, whose link you can find in the description of this video. And thank you so much for watching. We'll be moving ahead with some another interesting problems. Thank you so much.